Okay, so what about this? They want to know, everyone have a look please on this graph up here of this function. They don't give us any numbers or anything, but they want to know at which points is the slope of the curve negative. So A, B, C, D, and E. Which ones are negative? We'll color code these. So these will be blue. Where's the slope negative?
So in my mind, it would be A, B, and then D and E.
Okay, but now what you're doing is you're calculating slopes of secant lines, it sounds like. That's not what they're looking for. If we want to know where the slope of the curve equals slope of tangent lines. So where would tangents to the graph have negative slopes?
B and E.
So B would, right? So there's one. Oh, sorry, B wouldn't, what am I saying? When you say D would, D would and E would, right? See what I'm saying?
Yeah.
Okay. Where would it have positive slopes? It looks like at A, there's a slight positive slope. At B and at C, okay? List the slopes in decreasing order. I mean, we'd have to just go from biggest would be probably C, it looks like.
Yeah.
Then B, then A is a little less steep, positive slope, right? Then D is pretty negative and E is even more negative. Make sense?
Okay.
Okay. Okay, what else?
Number 5.
Number 5, okay.
On which practice?
1. For 1 practice.
Oh, I was stuck on that.
Yeah, I read this one too.
Okay, so we're gonna let's talk through this. I don't know if we're gonna do the whole thing because we're gonna have a really quick way to do this one as of today.
Yay.
We get a very good shortcut by the end of the period. But let's make sure everybody understands what's being asked and how we could accomplish that with what we know right now. Okay, so what about that? So we want to, it says use the definition of, no, and look what they're doing. They're using the other definition of a derivative that we talked about the other day. I don't care if you use that or not. You could use we could write this slope of the tangent line in terms of the f of x plus h minus f of x over h as h goes to 0. If you prefer, that's fine. Doesn't really make any difference, okay? To find the slope of the line tangent to the graph of f at P. Okay, so here's f of x, right? We're going to have to find the derivative using that arduous limit process. And we won't go through the whole thing, but let's at least just take a second and set it up. So if this is f of x, f prime of x is going to be the limit of what? 2 over, let's use the x plus h one.
X plus h
Minus
minus 2 over x.
divided by
H.
h. Everybody see that? Because this is right here, isn't this just f of x plus h minus f of x over h as h goes to 0? Okay, now, we're not going to go through the whole process, but what's our technique for resolving the indeterminacy of a limit like this? If I try to evaluate directly, I'm getting 0 over 0. What do I do if I've got complex fractions?
Make the top one big fraction.
Good. Simplify the top into one big fraction. Simplify the bottom into one big fraction, h over 1. Flip and
I
multiply.
think it was just like the f of x and f of a, which was like confusing, like I wasn't sure.
Okay, right. And that's,
They put it like-
so,
Yeah.
let's not, I wouldn't get too hung up on that. We looked at, I think you were here. You were gone.
Probably.
It's in the notes. We looked at an example where we did one using this alternate, there's just an alternate form of the derivative definition, right? All it does, and I'm going to do this in 2 seconds here, but all it does, this will help you out. All we're doing is if I've got some function, instead of picking the points to be x and x plus h that are defining our secant line, we would just pick them as being something like a and x. And then we're gonna let a approach x or x approach a, whichever one we want. They do this is kind of a weird, that's a little strange. Typically you'd have a approach x. Doesn't make any difference though, right? Either way, the strategy is the same, right? Just think about it conceptually. Our strategy is we want to take a limit as we draw those 2 points together so the secant line becomes a tangent, right? And that's our trick for finding the slope of the tangent line. Once we know what the slope is, if I wanted to calculate, if this is the point of tangency right here, what's the slope of the tangent line going to be given by? F prime of what? Everybody see that? Everybody gets that? We're going to evaluate the derivative function at the x value of the point of tangency. Don't lose sight, but this is such a hugely cool and important thing that we're able to take some function of x and do this magical differentiation process, and we come out with some derivative function of x, right? So what is the job of a function? When I plug in x values, it spits back the y values, right? What's the job of a derivative function? I put in x values, it spits back what's the derivative telling me when I plug in an x? Slope of the curve, right? Okay? So if I want to know what's the slope of the curve at that point right there, well then I'm going to plug in -5 into my derivative function. Okay? All right. What else? Time for a couple more. Choose wisely. Anything else?
I haven't done this.
We can. I'll tell you what. We'll take a little time. What did I put for due dates on these? 27th. These are pretty big assignments. How about if I make them due Tuesday so you can get any last minute questions answered Monday? And just, I mean, I know you're not going to abuse that. I mean, there's more stuff coming, so you want to get this out of the way. That way you can reserve, if you have any last minute questions, bring them in. We'll shoot them down on.
Are we just like looking today or?
No, I'm going to show you. I'm going to show you a trick today. This is pretty cool. This will make your lives a lot easier. You're going to like this.
How would you approach? How would you approach 15?
Okay, we can look at that.
Oh, never mind.
Okay,
I think
got
I
it.
figured it out. I was being stupid for a second.
Okay, so here's the stuff for today. Everybody, now click and close, and I want to get your undivided attention here for a second. I'm going to show you. This is one of the greatest tricks in mathematical history. I'm going to show you. This makes all those problems that I would say it's right up there though. It's pretty darn good. All those problems that, I mean, you're probably getting real tired of doing them. I tried not to assign too many, but maybe I did. I don't know. I'll make you a deal though. After I show you these tricks, if you feel like you've done enough problems finding derivatives using limits, I believe you. You can just use these tricks to answer them more quickly if you want to. Okay. But you can at least, at the very least, you can easily check your work. So let's take our goal here today, and this is really all we got on the docket for today. If we get a little further, that's great, but this would be fine. Is we want to come up with a generalized power rule for differentiating power functions. Now, what's a power function? Just a variable to a power, right? So x to the n, and we'll start off saying n has to be an integer, but we can dispense with that. We'll find out pretty soon, and n could actually be any real number, which is pretty amazing. Almost any real number. Yeah, can't be 0, but it doesn't work for that. But it can be almost any real number. So how do we go about doing that in calculus or in math in general? When we want to come up with a general formula, we have to start from a completely general place and just see where it takes us, right? So we're not going to specify anything. We're going to say f of x is just some power function, x to the n, x could be anything. So if we differentiate that, we're just going to apply our limit definition like we have in the past. Here's where we always start, right? We start with the definition of the derivative, and then we apply it to our specific function. So what are we going to get then? What are we going to get here? I used delta x here instead of h, that was kind of dumb, but oh well. They're interchangeable, delta x and h. What is this part gonna be? F of x plus delta x.
X plus delta x is the n.
Minus x to the n, okay? All over delta x as delta x goes to 0. Okay, now, do you see, is there something about that that seems a little puzzling? How are you gonna do that? How are you gonna expand out that binomial? We don't know what n is, right? If it's squared, we know what to do. If it's cubed, we know what to do. But if it's taken to the n, what are we gonna do? How many terms are there gonna be? Actually, there's gonna be n plus 1 terms. In an n degree binomial, nth power binomial, there's always n plus 1 terms, but I don't know what n is, right? But sometimes in math, we don't have to know all the terms, because there's a pattern we can establish, which is gonna do away with the necessity of writing down each individual term, right? So we could pull out the binomial expansion for this, but nobody remembers that. What you probably do remember, though, is Pascal's triangle, right? Anybody remember? Okay, so this would be a good day to review a little Pascal's triangle. Pascal's triangle this is one of those, if you really like math, this is kind of one of those like, almost like a game show math thing. I mean, it's just really, sometimes the patterns you see, numerical patterns in life, are just really interesting. Pascal's triangle is no exception. It does some pretty remarkable things for a pretty innocuous looking entity. I mean, all it is, you know how to make Pascal's triangle? From last year, from Algebra 2 probably. How do you make Pascal's triangle?
1.
1.
Oh, yeah. Okay, it's
And then we always add 1s to the outside, and then if there's any interior numbers, we just sum the numbers above,
Wait.
right? You get the idea? So then this is gonna be,
1, 3, 3, 1.
and then the next one would be,
1, 4, 6, 4, 1,
okay?
1, 5, 10, 5.
Okay, that's probably good. That gives us a bunch, right? And what is this thing really doing? Well, it's just giving us the coefficients in our binomial expansion, right? So if we have a plus b to the n, well, this is going to be the row n equals 0, right? This is going to be the row n equals 1, n equals 2, etc., all the way down, right? And these are the coefficients, and what Pascal's triangle does for us is it tells us, if we know the coefficients, the rest of the pattern is very simple, right? If we do something like a plus b, let's just do, for example, a plus b cubed, okay? A plus b cubed, we know the coefficients are going to be 1, 3, 3, and 1, right? Well, what are the coefficients being multiplied by? Okay, so it's going to be a cubed, and there's actually an invisible, we don't write it, but it's there. There's an invisible b to the 0 there, right? What's the next one going to be? A squared b to the 1. We wouldn't necessarily write the 1, would we? But it's there, right? So what's the next one going to be?
B squared.
B squared.
Yeah, so this one's going to be a to the 1, b squared, and the last one?
A to the 0.
Good.
Cube.
So what's the pattern then? What can you tell me about the exponents? What's our rule? What's the sum of the exponents for each term?
3.
3, right? Okay, and we're going to step down sequentially from all the weight starts off, the exponential weight is for the first term, and none of it's on the second term, and then gradually it just does this, incrementally just ramps down and up respectively, right? But they always add up to 3. Okay, so we could do this. What do you notice here? Look, I want you to see if you can see some patterns. do you notice any patterns in these coefficients relative to,
Your second, your second.
look at this, right? How about that? The second coefficient is always equal to n, isn't it? Everybody get that? And then the third one's a little more mysterious, and, you know, some years we take time and we try to figure it, but we won't even mess with it. I mean, we could, well, actually, can you find it?
2, 3, 4, 6, 5.
So can you figure out, here's the question, can you figure out how to get this one?
That's adding by like, just that.
How do you go from 4 to 6?
Oh, I'm talking about this going.
The first one, you add 2, and then you add 3, and then you add 4.
So are you seeing a pattern?
Yeah.
So you're adding, you can kind of look at what you're adding diagonally, can't you?
Yeah.
Right, everybody see that? So to get this one, we're adding that one. To get this one, we're adding, right? You see what I'm saying? So you can come up with a pattern that way. But, right, and so we could turn that into, you know, tell you what, we'll come back to that later. I don't want to spend too much time on that, because really it's irrelevant, because I'll tell you why. It almost reinforces the point. If we don't focus too much on that one, it almost reinforces the value of what we're doing anyway, right? So if we were to expand this out then, what does a plus b to the n look like? So now let's try this. So a plus b to the n. What's the first coefficient, of course, going to be?
1.
1. So we're going to get a to the n. What's the second coefficient going to be? N times a to the n minus 1 times b plus, we don't even care for now, some other coefficient that we could figure out what it is, right? If we wanted to make, and it's kind of a good exercise in inductive math to look into stuff like that, but not for today. I don't want to waste time on it. A to the n minus 2 b squared, and so on, right? Let's apply that to our problem. Let's apply that to this. If we're going to do x plus delta x to the n, you tell me when you see why we don't care. Why we don't care what the other coefficients are. So this is going to equal the limit of, we got to expand out that whole red thing, right? So we're going to get x to the n
Do you just want to use h?
plus, yeah, let's use h. So we're going to go, delta x is going to go to h, so it's just a little easier to keep track of, right? So x to the n plus n times, everybody agree?
Yeah.
N times x to the n minus 1 times h plus some coefficient, who cares, times x to the n minus 2 times h squared. We'll do one more, plus double, who cares, times x to the n minus 3 times h cubed, plus a whole slew of other ones, right? N plus 1 of them. We couldn't write them all down because we don't even know what n is, right? That's the red expansion. Yep.
If you don't know what n is, then how can h be squared and h to the third?
Well, that's part of our pattern. That we don't. It doesn't matter what
Oh,
n is.
yeah,
Right.
never mind.
Okay.
I get it now.
Okay.
Never mind.
So then minus x to the n. Are you seeing something happen? Over h as h goes to 0. Okay, well, I don't really need to have brackets around this because there's nothing to distribute, right?
Right.
Everybody agree? So do any terms disappear?
Yes.
Everybody see that? So look, the x to the n's are going to go away. Now, what do all the other terms have in common?
An h.
We can factor an h out, right? So what happens when we factor that h out? We got an h out front. What's left behind when we do that?
And
x
and
N x to the n minus 1 plus
plus
all the other stuff.
plus h times, because if we factor an h out, I'm left with an h there, right? H who knows what the coefficient is? X to the n minus 2 times, I gotta make this a bright color that really sticks out. I guess we do that one, that's right. Times h plus some other unknown, who cares, coefficient times x to the n minus 3. So how many h's are left from this term if I factor an h out?
2.
H squared plus et cetera, right? All over h as h goes to 0. Okay, well, what's the magic there? What happens that makes this thing work?
The h's count.
The h's cancel. Okay, good. When the h's cancel, now we can take our limit, right?
There's the
The h's are gone. Now we can take our limit as h goes to 0. And why did I not even care about those coefficients?
Because they all go to
H's.
They
0.
all have h's in them, right? So what do we even care? The only term that is not going to have an h left over, at least an h to the first power, when we factor an h out, is the first one, right? So in the limit that h goes to infinity, all of these terms, all of them, all n of them that are remaining, go to 0, and we only end up with one left over, which is that guy. So we got our answer, right? So f prime of x is equal to n times x to the n minus 1. There's our generalized power rule. How about that? So we'll put a box around that. So a lot of times the way we show that, like in a calc book, is we do something like this. The derivative with respect to x of what? Of x to the n is equal to n x to the n minus 1. Does that notation make sense? We're taking the derivative of this, and that's giving us that answer. Okay? We'd say that the language would be the derivative with respect to x of x to the n equals n times x to the n minus 1. That makes life so much easier. Let's apply that in some cases. Like for our general, so there's our general power rule, right? Now, I'm going to add one thing to it here before we move on. What if I had a constant in there? Doesn't change anything, does it? If I had a constant in there, I would have just, when I went through this whole process, I would have just had that constant in each term and I could have factored it out, right? So we can see that also. Like if I had something, f of x equals cx, well then f of x plus delta x would have been c times x plus delta x, right? C times f of, hang on a second. Oh, there we go, yeah, c times x plus delta x, right? And to the n, what the heck, what did I do here? That isn't good, right? Should be an n there, shouldn't there? Oh, not if I do cx, never mind, yeah, never mind, never mind, I'm right. Minus c times x. Now look what happens. If I do the math and I distribute the c, what's going to happen here? It's just going to be in each term, and so why couldn't I just factor it out in front of the whole thing? I can't, right? The moral of the story is, when we're taking a derivative of a constant times a function, and this is huge, this makes life really easy, we can always, and this is the language of calculus, we'll just pull the constant out front, right? So we could just say that what that's equal to, the derivative of c times x to the n, is just equal to c times the derivative with respect to x of x to the n, right? So what do we get from that? Well, that's our general power rule. The constant is just going to be multiplied by the result. You can always pull a constant out front when you differentiate, okay? Very handy, okay? So, okay, anyway, that's if you want to look at the work, I'll put that in the notes if you want to follow it all the way through. But the important thing to know is it just ends up coming out front, okay? So let's apply this in some cases. What if we had something like, just a reminder of the notation, we could say f of x, start with f of x, we'd say f prime of x. If I start with y, I would say dy dx, or I could say y prime. So I'm giving you a function in y equals x squared form. What's the derivative?
Y
Mhm.
is two.
I could do y prime, or I could do dy dx, either one, right? Let's just say we're doing dy dx. What's my rule? What do I do?
The two goes,
X,
Yeah, the 2 goes down front, doesn't it, right?
2x to
The n goes down front, and I subtract 1 from the exponent, right? So we just get 2 times x to the 1, 2x. Okay? What about down here? What's y prime?
the 3x to the square.
Is that easy?
To the square.
What's the answer here?
4x to the third.
Okay? So those are, pitifully easy ones, but we can also apply this to some that don't look so easy to begin with. What about that guy? We looked at this one at the beginning of the class, and that's a little bit of work to do that limit, right? How could I rewrite that in a way where I could apply the general power rule? In order for this to work, I have to be able to write it in this form, some constant times x to a power. It has to be exactly in that form for this derivative rule to apply. That's the game we play with differentiation. We're going to come up with a whole
Did you
list,
say-
a short list, of some really common derivative rules. And most of the time, most of calculus is not taking the derivative, it's kind of setting up the problem so it fits the derivative. How could I rewrite this one?
2x, or 2
Two
times x to the.
There you go, right? So we'd have to write this as 2 times x to the minus 1. Now it fits the rule, right? So what's the derivative of 2 times x to the minus 1? Well, we multiply the exponent by the coefficient, right? So I'm going to get a negative 2x to the
Negative,
negative 2. I subtract 1 from the exponent, and I get that. So if I wanted to write that as a rational function, I just get negative 2 over x squared. Okay? How about something like that? I mean, that's no big deal, right? Really, that's just when I see stuff like this, if I see a constant on the bottom of a function, that's just a denominator of a fraction that I could pull out front, right? So really what I'm doing is I'm pulling the 4/5 out front and taking the derivative of t squared.
Yeah.
Okay, so what's that going to give me then?
Um,
I'll write it that way, I guess, first of all. Okay, so I'm going to bring the 2 down. 2 times 4/5 is
8/5.
t to the 1. No big deal. Okay? What about that?
This is easy.
Radical. Yikes.
No.
2x.
Those are much harder to deal with limits, right? So how can I write that as a power?
2x.
2x. There you go. So it's 2x to the 1/2. So when I differentiate, what do I get? 1/2 times 2 is x to the, good, 1/2, hang on. 1/2 minus 1.
Is negative 1.
Everybody see that? Okay. And so if I write that without a negative exponent, it would just be 1 over square root of x. Right? But remember that when we have a negative exponent, what a negative exponent means, it's positive in the bottom. That's kind of how I always talk about that with my Algebra 2 classes. Whenever you have a negative exponent, the negative exponent becomes positive in the other part of the fraction. When I say other part, I mean numerator versus denominator. If it's a negative exponent in the bottom, it's positive in the top. If it's a negative exponent in the top, it's positive in the bottom, right? What about that one? Now I got to rewrite it first, right? That does not look. That doesn't look like this. That doesn't look like cx to the n. It's got to look like that before I can differentiate.
2x, 2.
2x to the 2 is
Okay, but now where's the 2? The 2 has to stay on the bottom, right? It's a 1 over 2. So this part right here is going to become just a plain old 1/2. But
Then you're gonna get 1/2.
okay, so now x to the 2/3, the 3 goes on the bottom, doesn't it, right? Whatever the index of the radical, that's going to be the denominator of the rational exponent, and the 2 is the top. I think we talked about that earlier in the year, we reminded ourselves. And it's in the bottom of the fraction, so the whole thing is, okay. So does it make sense that that's x to the negative 2/3? Okay? So what's that give me then? Negative 2/3 times 1/2 is,
Negative 2/6.
okay, negative 1/3 if I reduce it. X to the, what's negative 2/3 minus 1? Negative 5/3. So we would get negative 1/3x to the 5/3, or if we want to write it as a radical, negative 1/3 times the cube root of x to the 5th.
Yeah.
Okay, good. Okay, what about that? What do you think I'm going to do there? If I've got f of x equals a sum of terms. Okay, right, now that's a derivative rule, and we'll talk about a list, not today. Today we just want to kind of get through, power through the power rule here, but I'll give you a list of derivative properties that you already know, because they're so intuitive. Doesn't this make sense if we think about how we calculate derivatives? We calculate derivatives from limits, and what did we do if we were taking the limit of a string of terms? Took them individually, right? So we're going to do the same thing with derivatives. And the way you say this in calculus is I'm going to write this down, it's so important. If we differentiate term by term. Okay, so we can take each term one at a time. We'd want to, well, let's see if we can do these without even rewriting them. So what's this first one going to be?
Negative 2x.
Because I've got a negative 4/2, so I get a negative 2x to the third, and then plus, what's that going to be? 9x squared minus, so I've got an x to the 1/2. Would that become 1/2 x to the negative 1/2? And a negative 1/2 is just the square root on the bottom, isn't it? Right?
Yeah.
You see that? Okay. All right. I think we'll stop there. I don't want to give you any more. I think that's pretty good. So I'm going to give you a short assignment just to practice the power rule a little bit, and then we'll launch into some other stuff next week. Does that make sense?
So it'll be another assignment.
Yeah, and it'll be short. I just to kind of reinforce some of these very simple problems we're doing, just so you ironed it into your brains.